Okay, we now move to the first of the case studies that is given at the back of the practical called Using Filters to Determine Colour Index, also known as the False Colour Index prac. Here we are given a table which has data. The data is the apparent magnitude, the absolute, the colour index and luminosity class. We'll be using this information in conjunction with HR diagrams and other tables and charts that we have got to determine as much information about these stars as possible. Firstly, let's work out, we can compare we can find a few things straight away about these stars. Let's first work out what the first thing we can do. So the first thing that we can do is the distance. Now, the distance is given by the formula d equals 10 times 10 to the apparent magnitude minus the absolute magnitude divided by 5. So we can work out the distance for both of these stars because we've both got the apparent and the absolute magnitude. So I'm going to do it for Alphen and then I'll ask you to do it for Beten. So the distance to Alphen from the Earth is going to be equal to d is 10 times 10 to the, now it's m minus m on 5 would equal, it's little m first, so it's minus 2.6 minus 3.1 all over 5. And if we just type that into my calculator, as I reach the calculator here, I'll just pause it while I get the calculator. Okay, we've got, I have got negative 1.14. That's a negative sign, negative 1.14. So this is negative 1.14. Okay. And all we now need to do is type that into our calculator and get the d in parsecs. So I'll just do that now, and I've got that as 0.7244 parsecs, which we'll just round to 0.7 parsecs there. Okay, I can also work out how many light years away, because I know that 1 light year, so 1 light year is equal to 3.26 parsecs. No, sorry, I'll try again. That's good. 1 parsec is what I was trying to say. 1 parsec equals 3.26 light years. That makes much better sense. Okay, so just rubbing that out. Okay, so now I've got that information. I can just multiply this number by 0.7 by 3.26, and I've got that in light years, which is 2.4 light years. Okay, if you just take a few moments now and use these two numbers for Beten, you can now find the distance to Beten. So don't forget, in the modulus up here, in the index, it's the apparent magnitude minus the absolute. So it's always this number here minus this number here. Okay, take a few moments and do that now. Okay, using these numbers here, we've got a negative absolute magnitude, which means it's really, this star Beten is a very bright star. And we also have the apparent magnitude here. So in the modulus is 8.2 minus negative 7.4. So these two actually add together. And dividing it by 5, you get an index here of 3.12. Now that's quite a large number. That's 1,320 approximately. So we times it by 10 and we get 13,000 and so parsecs. And then multiplying by 3.26, you can determine the distance that Beten is in light years, and I've rounded it to just 2 significant figures there. Okay, so that's the first thing that we can do with this information. Now the second, we can compare how bright they appear on the surface of the Earth. So we compare the apparent brightness. So comparing apparent brightness, we can use it by the formula IA on IB is equal to 100 little m minus, well, MB minus MA on 5. Okay. Now, I like using this formula in a different way. I just try to work out this part up here. Now, this part, let's compare the brightnesses between alpha and beta. The two values that we're going to look at is 8.2 and negative 2.6. We always start with the larger value, which means it's the dimmest star. So we're going to subtract them, and when you do 8.2 minus negative 2.6, that's an addition, you get 10.8. Dividing that by 5, you get 2.16. So this equals over here, I should change the colour, equals 100 to the 2.16, which equals, if you just do inverse log of that answer, you get 144 or 145 approximately. Okay. Now this means that one of these stars is 145 times as bright as the other. Now we have a look at it. The brightest star will be Alpha, as it appears to us. It's not truly the brightest star. It appears bright. And Beta is a dull star. It's not truly a dull star, but it appears. So we can write, therefore, that Alpha appears to be 145 times, that's 145 times, as bright as Beta. I'll make that Beta. Okay. But that's only as it appears on the surface of the Earth. Now we can work out what their true comparative brightness is. To compare how they truly are bright to each other, we can use the absolute magnitudes over here. So we'll use that one there. I want you now to take a few moments and compare their absolute brightness by using these two values instead in this formula here. Okay. Okay, let's see how you went. Alpha has a magnitude of 3.1, so I'll put it on the top because it's a more positive number, and Beta on the bottom. I subtract them and you get the difference in magnitudes as 10.5. Dividing that by 5, because the formula requires you to have m minus m divided by 5, so mb minus ma, that's the duller star minus the brighter star on 5, you get 2.1. So the answer here would be the comparative brightness is 100 to the 2.1. Now if you just do 100 to the 2, that's 100 square, so that should be, I've done that wrong, so I'll just rub that out. Yeah. Okay, so it's 100 to the 2.1, so 100 to the 2.1 equals, and the answer is 15,848, which we'll just round to 15,850 times. Now, which is the brightest star? Well, Beta is the more negative, so therefore this is it's the brightest star. So Beta is about 16,000 times as bright as Alpha. Okay, so we can compare those two, just the two stars. So that's the second thing that we can do with these stars. The next thing we can have a look at is the colour index. Now the colour index tells us a few things. From the colour index you can actually get the colour. Let's just do that one. Colour. Now the colour is given by the colour scale, remembering that a plus 2 is red and a negative 0.5 is a bright blue and a 0 is a white. So we can estimate just here that it's a little bit more than, this Alpha is a little bit more than 0, so the colour of Alpha would be reasonably white. Beta is a 1.5, so it's halfway between here and here. So we can estimate, we can actually go to a colour chart if we would like to, but I'm just going to do it off the top of my head and see if I can remember it. I would suggest that 1.5 is probably orange. Now I can have to check that, but I'm pretty reasonably that it's an orangey coloured colour, because in a few more moments I'm going to work out where it is on the Hertzsprung-Russell diagram. So that's the first thing that we can work out. The second thing that we can use for the colour index is actually the temperature. To work out the temperature, I need a colour index against a temperature chart. And I'm just going to pause the video now and get one up so that we can have a look at one. Okay, so here is a version. This is the one from the notebook, and the colour index against temperature chart. There's a few of them that are available commercially from different sites. So this one here, we can use this chart simply to work out the temperature using the colour index. It's quite detailed here. So looking at the actual value that we're going to use, let's start with alpha. Alpha is a 0.2 colour index. So going through and having a look, let's get through that. 0.2 is there, okay? And if we just read sideways, that's 8,000 K. So we can determine the temperature of both stars by simply going through and having a look at that. So I want you to take a few moments now to determine the temperature of Beaton given that one there. Okay. Now that you've had a look at the temperature of Beaton, we can now have a look at what else we can do with the colour index. So far the colour index can tell us the colour itself, and it can also tell us the temperature. Now, apart from that, we can also have the spectral class. Okay? To do that, we will need a HR diagram. So we now need to have a look at a HR diagram. So let's get a HR diagram up, and we'll just pause while I do so. Okay, now we've got the ready for the HR diagram. We can get our spectral class. You could simply just use a chart which has the temperature against class, but let's use the HR diagram. So here's the one. This is the class HR diagram, and we just worked out that this was an 8,000 Kelvin star. So looking at 8,000 Kelvin, 8,000 Kelvin is here. So we are looking at an A-class star. Now, we could have interpreted that it's an A-class star straight away. So let's go back and have a look at, what did I say the colour was? The colour was, remembering a colour index of 0 equals white. And we know that a white is an A-class star. So we can be quite, just off the top of our heads, say that that one there is a A-class star. But being able to work out what Beaton is as a 1.5, let's have a look at what 1.5 would be. Now 1.5 is a line which goes up here, and we are between K and M class stars here. This is not a linear scale here, so it's somewhere between a K and an M star, and it's around about 3,500 Kelvin. So we can use the colour index then to determine what the temperature and the class of that star is. Okay, so that's using the colour index over there. Now what else can we determine? Well, the next thing is we can determine using the luminosity class. Well, the main sequence. We know where the main sequence is. The main sequence is a band going through there. I'll just get a nicer diagram up for us. So let's just clear our annotations here and get some, there's a horizontal line there and a vertical line to put our Hertzsprung-Russell diagram on. Okay, so the main sequence is a band going down like that, and alpha is a A-class star that lies on this band. Okay, so we know that it's a class A. It's reasonably bright, and so on. Next thing is we're going to look at Beaten. Now, Beaten is a 1A superluminous giant, so it's no longer on the main sequence, but we know it's a reddish colour, so it's up in this point up here. So these are the red giants. So what do I know about these two stars, Alphen and Beaten? Well, I know that if it's a main sequence star, then it is actually fusing hydrogen into helium, and it is it's a normal star that is being born, and it's on the process of just going through its life cycle. But if it's a red giant, then I know that this star here is starting to fuse helium into the higher elements as carbon, and then nitrogen and oxygen, and finally into iron. So the red giants are stars which are on the way out. So these are dying stars. We also know that a superluminous giant, the massive red giants, they are of large diameter. These are massive stars. They have swollen from being their normal size as a main sequence, and they have become absolutely huge. And as they swell, they become more red coloured. So this red giant is a very large star. Now, A-class stars like Alphen up here are still large, but compared to the superluminous giant, it would be quite small. So that's two things. Another thing is we can talk about density. Large stars are less dense. So we can also say a few things about the less dense. So just getting some clear objects, clear annotations, that we know that this would be a less dense star, and this would be a dense star. Now when we say dense, not hugely dense, not as dense as a white dwarf, but it's still less denser than the other because we're comparing the two stars. We can also say that certain features, the absorption lines on denser and less denser stars, become thinner and thicker as you get pressure broadening. So on one of the stars here, we have a thin absorption band, and the other one we have a thicker absorption band. Okay, yes, so sorry. Therefore, this is the main sequence star would have a thinner band, and we'd have a larger, thicker bands in the less dense stars. So that's another thing that we can work out from these two this data up here. Okay. So in summary, let's work out just after a first cursory thing what we have what we have clearing the annotations, we say, what we have discovered using this data. Okay, we can find the distance to the stars in both parsecs and light years. We can compare brightnesses as they appear or as they truly are. We can either compare them with these two here, or we can compare them with this two here. So this is comparing their real brightness, so absolute magnitude would be real brightness, and the apparent bright ones would be as they appear. We can use their colour index, and the colour index can give us three things. We can actually get the colour, we can get the temperature, and we can get the spectral class. Don't forget that the spectral class itself can give us, the temperature can also give us the spectral class. And if we know the spectral class, we can also work out the features of the spectrum. These are things like certain absorption lines, the presence of titanium oxides and so on in the core of stars. And finally, we can work out their position on the HR diagram, and that means we know where they are in their life cycle. We know what is happening as their fusion in their core, and we can also compare their density. So just from this little information alone, we've come up with a hell of a lot of information about these two stars. Thank you for watching.